Fantastic. So this brings me now to the grand finale of the first third of the course, the first part of the course. And this is the strong form of the solid mechanics problem. Okay. MSY 310 students, you would have seen this, I believe, with Dr. Ingels, but MOW27, this might be new, but it's not a problem because this is really just a summary of exactly what we have done before. Okay. But it's all just in one page, and I just want to make sure that you understand that what we need to do. So first off, let's look at the unknowns of this problem. And so the unknowns to this problem are, we need to have these three unknown functions, u, v, w, which are spatial functions over the body, completely spatially. For each x, y, z point, we need to know what is the displacement in u, so in the x direction, the displacement v in the, so that's displacement in the y direction, and w, the displacement in the z direction. Okay, so this is important to understand, and it's spatial functions. So they are quite tricky. They're not just a number, they are functions that will define everywhere what's going on, like we've done now quite extensively. You should be now very comfortable with this. That's three unknowns, okay, but they are functions. Then the strain matrix is another set of unknowns. But because it's symmetrical, we have the three on the diagonal and the three off diagonal on the top, because these three on the top diagonal is the same as the lower diagonal. That's why we could write it as a 6x1 vector. But that is 6 unknown functions that we have there with the strain matrix. Okay, so that is now 9 in total. And then we sit with the stress matrix, which is also symmetrical by construction, the way we do it now in this course, is essentially bringing us up to a tally of 15 unknown functions. But there are spatial functions over this domain that we have to try and approximate. So if we have 15 things that we try to approximate, we need 15 equations that we need to satisfy. So let's see, where does these 15 equations come from to satisfy these 15 unknowns. So first off, the equilibrium equation, the divergence of the stress tensor plus the body forces, gives us 3 partial differential equations. Okay, so these are 3 equations that helps us to solve this, but they are partial differential equations. Then we essentially can map our strain response to our stress via this algebraic equation. Okay, and that was 6 equations because we had a 6x1 stress matrix. Let me just go back here to the textbook. Just as a reminder, when we wrote this, just going to make it clear. There's the strain, there's the stresses. 1, 2, 3, 4, 5, 6 equations. And if you think about this, this will get multiplied by 6x1 vector. This is a 6x6 matrix. So there are 6 algebraic equations, yeah, that define what's going on. This represents the 6 algebraic equations that define what is going on there. Okay, so the important thing is that this is another 6, so we're now at 9 equations. Okay, and then essentially what we have is we have the strain matrix is given by this. Okay, displacement gradient plus its transpose times a half, sum of those two times a half. But if you think about this carefully, how many equations does it represent? It's a matrix, 9 components equals to 9 components. But only 6 of those 9 components are unique because of the symmetry. And so essentially this is only 6 unique partial differential equations that you will recover from this. You might at first think it's 9, but just remind yourself, if you repeat an equation, you're not adding information by repeating an equation. And so the off diagonals would be repeated if we were to falsely think of it as 9. But what we're ending up with now is 9 here plus another 6 is 15. These are the 15 equations that we can use to satisfy these, to try and solve these 15 unknowns. Okay, and then in addition to this information, what we also have is that everywhere where we have prescribed tractions, like there or there, the stress tensor dotted with the normal to that surface must be equal to the attraction that we claim that we've specified there. Done. Okay, so that is it. And if you want to go one further, we can integrate those tractions over the areas, or with the moment arms, or with the torque arms, and compute the normal forces, shear forces on those faces, and the moments and torques on those faces. Okay, so that is important to understand, that we can then leave it as tractions, or we can take it further and say, let's compute the stress resultants. And then lastly, we have essentially here where we have prescribed displacements. So this is indicated by the U bar. So U bar is where the prescribed displacements are. We must make sure they are satisfied on the places where we have prescribed displacements. So what is important to understand is the entire surface of this body is given by the union of where we have prescribed tractions and prescribed displacements. Because what you have to not forget is, if I say that there's no traction applied there, then it's a prescribed prescribed traction of 0 there on the surface. So if you look at this surface here, there is SU. This is where I've defined prescribed displacements. Okay. Here is part of my prescribed tractions. All of this. But these are mostly 0. There's a couple of places where it's non-zero. That is important to understand. Okay. So when I ask you to check for the prescribed traction, I ask you to check also where there is supposedly 0 tractions, because that's a prescribed value, it's just 0 there. Okay. The other thing that is important to understand is, this is, I just want to make clear that we're just comfortable with this. Okay. Where I have a prescribed displacement, they will follow a traction there. Okay. We don't put a prescribed traction there, we put a prescribed displacement, but after we've solved the problem, we can go and compute what is the reaction traction there to make sure that this was indeed 0. So if I were to pulling on this potato, pushing and pulling and twisting the thing, the reality is that this would result in a reactions here. And all that I'm specifying is just the prescribed displacement must be 0, but I can after the fact go and compute what was that reaction traction. Okay, that is one important thing. The other thing that's important is everywhere else where we have prescribed tractions, whether it's now 0, non-zero, okay, the displacements will follow, as well as everywhere inside the structure. But the point is, where I have a prescribed traction, whether it's now 0 or some value, doesn't matter. The displacements will now follow there. Okay, so we still have tractions and displacements everywhere in the structure after we've solved the thing. But the way we start solving it is, some places we'll only specify the displacements and then we'll compute the reactions, or other places we'll specify all the tractions, whether they are 0 or not, and then they will compute the displacements. Okay, so that is just to make sure that we're comfortable with that. That is a very important point. And just think about it when you think about even your structural mechanics stuff that you've done. Wherever you had a prescribed displacement boundary condition, whether it was a clamped beam or a pin joint beam or something like that, at those places where you have prescribed displacements, we had those constraints. That's where the reactions were. Okay, and that's where you computed your reaction forces. So everything is consistent still with what you've done in MOW to say nothing has changed. Okay, so 15 equations, 15 unknowns. Now you understand the strong form for the solid mechanics boundary layer problem. But I can be straight out with you. This is a hell of a hard problem to solve. So hard that we can't solve it exactly. We can only approximate it. So what the rest of this course is going to be, the next third of the course. So we're now 1/3 into the course. The next third of the course is going to be, how do we approximate this? Okay, and what I'm going to tell you is, just to give you sort of an understanding of where we're going to go, we're not going to approximate this problem exactly. We're not going to solve this problem exactly. We're going to approximate it. That is important to understand. As a matter of fact, as I'll show you later on, we're not even going to satisfy this equation exactly. But what we're rather going to do is, we're going to say this continuum mechanics or this continuum problem is way too tricky for us. Okay, but what I'm going to do is I'm going to approximate even this. This is essentially what I'm going to do. Is I'm going to construct from the strong form what's called a weak form, where we will approximate this only. So we'll only approximately solve equilibrium for the continuum problem. But the way we're going to do it, this is the amazing part, we're going to transform this continuum problem into an algebraic problem. Yeah? And that algebraic problem will satisfy equilibrium exactly for. And so what's going to happen is, we're going to take a continuum problem that is so difficult to solve, we're going to say, let's transform this continuum problem into an algebraic problem, a system of linear algebra equations. But the beauty of that problem is we're going to exactly satisfy equilibrium for the algebraic equations. And once we have solved the algebraic equations such that they satisfy equilibrium exactly, then what we have is we have sort of the best approximation for equilibrium for this continuum problem. And this is what the finite element method is about. Because, as you've seen now, working with functions of x, y, and z, and all these things can be quite tedious, and they're calculus orientated. What works like on a computer is definitely working with algebraic equations. It's a lot simpler to work with. So we still have to do a bit of work to get there, but transforming stuff to algebraic equations is a lot simpler. If I can just demonstrate this point clearly to you, who finds this equation simpler to work with than this equation? And I think all of you are quite comfortable with this. And these are the algebraic equations. These are the partial differences. They take a bit longer to get used to in the beginning. But these algebraic equations, they just pop out. They boom. They're lekker. So the bottom line is please understand that we'll solve these algebraic equations of this problem that you stated here in front of you. And so everything that we're going to start doing then is going towards approximation of functions in the beginning. And then essentially what we're going to do is we're going to be discretizing stuff more and more and more. And essentially that discretization allows us to get from a continuum mechanics problem of fields to sort of a algebraic system of equations that we can solve. And it still represents fields, and it's still the fields that we're solving there. We're just solving the fields at specific dots and points such that the rest of the field will be implied based on some assumptions that we've made. Okay, so hopefully this gets you excited about where we're going. But this is sort of the first part of the course. I also want to just maybe we'll do one thing and show you where in the textbook we are at the moment. Because this is the shocking thing. Okay, let me start from the beginning. So we've done this. Okay, stress and equilibrium. This is essentially what we have. Okay, boundary conditions, strain, this stuff, all of this stuff we've done now. Boom, nice. Temperature effects we could do if you wanted to. It's trivial to put in. It's just essentially the strain due to temperature that's unconstrained, and then the difference. But we're not going to worry about that for now. But it's really easy to do temperature effects. But the bottom line is where we are now is the strong form. And unfortunately, this textbook doesn't give us the system of equations that we're going to be solving like I've showed you in that concept card. But the reality is here's where things will start to get approximated. And in this textbook, there's a couple of things. There's potential energy kind of approaches. Let me see, where's the other one? There's some Rayleigh-Ritz solutions. There's the Galerkin's approach. So let's see if this is the latest edition, the fourth one. This is the third edition. I can't recall now which edition of the textbook this is. Anyway, but the point is some of the textbook will have, I think the latest textbook should have the different versions, like a Galerkin's method, Rayleigh-Ritz method. So what we're going to be doing is closer to the sort of the Galerkin's method, but what we are essentially going to be doing is just solving this with the weighted residual method. Okay, so the method we're going to use is going to be the weighted residual method, and it's not going to be potential energy. And the reason for that is just the weighted residual method is a lot simpler to understand. Okay, but this is essentially where we're going to be going towards, is to start working towards this approximations. Okay, so hopefully this gives you a good idea, but please make sure you understand this is the problem that we're going to be now approximating, all in one go, all in one place, and I look forward to the next part of the journey. Thank you.